Hello, humans. Ah, happy Friday, everybody. We are Fridaying here at the Campbell House. Uh, it's 7:21 right now. Got up a little late this morning, but in about an hour or so, both of my boys are going to be up. All the cats are going to be cranked up. Honey, we bought a zoo. So it's going to be pretty popping over here in a little bit. So I'm going to try to get this lecture in for you guys for the weekend because I know y'all are just like, where's my lecture? It's the weekend. Friday's here. And it's time to lecture, to watch over and over and over and over again. So check this out. What we're going to do, we're going to have a little blast of the past. We are doing Newton. We're on Newton. And I'm going to expand on Newton's second law. But I'm going to bring up something that we did in 310 because I've been preparing you guys for this lecture. Remember in 310 where we looked at exercises and muscles and we broke the ranges of motion into phases, right? Speeding up, constant velocity, slowing down. And in 310, I taught you guys to recognize who's greater than who. In other words, who is responsible for speeding up, who's responsible for slowing down, and then obviously if it's the same, they tie. Some of the things I used in 310 is like you're moving furniture. Let's say you have a big bookcase and you're moving it in the house and it's carpet floor, so it really emphasizes the friction. What's the hardest thing about moving it? It's getting it going. Speeding it up is the hardest part. Keeping it going isn't as tough. And slowing it down is even easier because you just let off and friction slows it down, right? So we did those kind of things in class. We applied that to exercises like think of the leg extension machine. You know, I hate that term, but you know what I'm talking about. But the knee extensor machine is the term I like to use. Think about it. We're going to speed up the extension, constant velocity of extension, slow down the extension, speed up the flexion, constant speed of flexion, slow down the flexion. There's my plyometric sequence, slowing down the flexion followed by speeding up the extension. That kind of stuff, right? That's Newton's second law, where it takes unbalanced forces of some force from some object has to be greater than maybe another force from another object. And if there's only one force, then it automatically makes it greater. Only unbalanced forces can change the position over time, thus change the velocity over time, thus accelerate an object with mass. It takes unbalanced forces. So not every force causes an object to speed up or slow down. Not every force causes a change to an object's motion. Only unbalanced forces, leftover forces. When I say leftover forces, I mean something has to be greater than something else. And if there's only one force, then that has to be greater. So you have an apple and you drop the apple, there's only one force, that apple is going to speed up. And one thing that's cool, maybe you guys heard of terminal velocity, like when skydivers are just, they don't look like when I free fall, I'm like, arr! When skydivers free fall, you just look at them like, hey, mom. And what's happening is cool. When they jump off, they're accelerating. They're getting faster and faster and faster, and they're like feeling it. But as they fall faster, the wind is pushing up more and more and more. Just like when you're going in a car, the faster you go, the more the wind pushes back on you. Until there is a speed based on their surface area where the wind is pushing up on them at the same force as planet Earth is pulling down on them. So that's cool. You don't free fall the entire time. Free fall. You don't continue to speed up the entire time. You're free falling, but you don't speed up the entire time. There comes a speed at which the wind is pushing up on you with the same amount of force as planet is pulling down on you, and you're at a constant velocity. You're at a constant speed. That's what orbit is. Orbit is a constant speed. That's why you're moving, but you're moving at the same speed, so you don't feel like you're speeding up or slowing down. So today we're going to get into more applications of Newton's second law. And the cats are starting to be active. They look like they're stalking me, like as a pack. keep you updated. So first thing I'm going to talk to you guys about is proportionality. And that's this picture right here, okay? So F is equal to ma. Force is vector, so direction matters. A is vector, so direction matters. So notice what I did here. The sum of the forces in a specific direction, in the x. So x direction, we'd be looking at across forces. So whatever the object is, the sum, I forgot to put my little thing, the sum of all the different forces only in the x can be responsible to change an object's motion in the x. So I hinted that last lecture. X forces cannot influence y motion. Across forces can't make something speed up in the up-down. And vice versa, up-down forces can't make anything change direction. Horizontal forces, we do in vertical forces. And I laid the foundation. Next week, we're going to do our trigonometry. I laid the foundation that 99.99% of forces have a combination. What? Hey, I know. Life is tough for a cat in our house. One time my dad said that if he doesn't believe in reincarnation, but if he did, he'd want to come back as one of my wife's cats because they live the high life. Be right back. Gotcha. You are free. Set free. All right. Oh, where was I? Some of the forces next. So that's why trigonometry to biomechanics is important, because we understand, let's say this cap of the pin is an arrow. So I'm pointing this. We understand that in the regular Cartesian plane, remember that from physics, you should have physics 207 or an equivalency. The Cartesian plane put our straight line directions, right? You had, let me draw the Cartesian plane real quick. It got its name from a medieval dude named Descartes, and he was trying to explain a spider on a ceiling. I mean, and he was like, how could I explain where the spider is on a ceiling? And then he came up with dimensions. So that's the whole, you have dimensions, the x and the y in 2 dimensions. Z comes out at you for depth. That's why 3D, you could see the screen up, down, left, right, and front, back. And think of this as roads. So like you have Interstate 10, that's one road, that's one dimension, but you could travel east or west on that dimension, some 310 stuff. So the x dimension, you could travel 2 different ways. You could positive x and the negative x. Same thing with y. Now, what I'm trying to get you guys to see is that only x forces can influence motion on the x road. Only y forces can influence motion on the y road. That's why x forces influence x motion, y forces influence y motion. So what if we get a force that's in a combination, which majority of forces are? Think about it. In order for you to apply all of your influence, or something else to apply all of its influence, all in one direction, perfectly, east, west, north, south, positive x, negative x, positive y, in a 360-degree window of possibility, there's only 4 degrees where all of the force is in one direction. Think about it. 4 times out of 360. And actually, it's worse than that, because we could go to sub, 1 degree, 2 degree, but we could do a 0.5 degree, 1.5 degrees. So really, there's infinitely many, but only 4 times. So majority of real life, these forces are going to be applied at a combination, is what I'm trying to get to. All of your force isn't always going to be perfect. It could be majority in one direction, but majority of real life, we're going to have these combinational forces. And so what we have to do with trigonometry is say, hey, this force, the cap is the arrow, this force is in a combination of positive x and positive y, northeast. Some of that force is being applied in the x, and some of that force is being applied in the y. But if all I did is give a resultant, that's the so what force, let's say a force of 200 pounds being applied in this quadrant, I need a way to be able to extract, to say how much of that force is X and how much of that force is Y, because only X forces can influence X motion, only Y forces can influence Y motion. So I have to be able to extract the components, the vector components of that resultant force, and that's what trigonometry does for us, okay? So I'm planting that seed for you guys, okay? So let's get more into depth for F is equal to ma. F is equal to ma. First of all, any equation is a proportionality. It's a relationship. In this case, I put something real simple. 20 is equal to 20. Duh. But notice, this is where direction matters. I can't say negative 20 is equal to positive 20, right? I can't say this. That's not the same thing, right? So again, direction matters. So the first thing I need you to notice is that with this equation or this relationship, whatever is on the left side, whatever number we get here, has to be the same direction as the number we get here. That's the first important thing. If this side is positive, in other words, a positive directional force, the acceleration has to be positive, a positive acceleration. If this is negative, this has to be negative, because positive 20 has to equal positive 20, negative 20 has to equal negative 20. So the signs have to be the same here, okay? They have to be. Direction matters with vectors, okay? That's the first thing. The next thing with equations is that whatever's on the left side is directly proportional to the whatever's on the right. Meaning, if 20 is equal to 20, if this side goes up to 30, this has to go up to 30. As this side goes up, that side goes up. As this side goes down, that side goes down. As this side goes down, this side goes down. As this side goes up, that side goes up. Say that 5 times real fast. They are directly proportional to the acceleration given the same mass. What I mean by given the same mass? Well, the baseball is going to have the same amount of stuff in it, right? I mean, I'm not talking like micro little granules, but for the most part, I weigh it now. It's going to weigh the same in a little bit. So the more unbalanced force that I give this ball from my hand, it's going to be proportional, directly proportional to the type of speed up magnitude or acceleration, and m is for the mass of the ball. As this side goes up, that side goes up, okay? 20 has to equal 20. Now let's look at how we can look at that in different ways. 20 also equals 10 times 2. That's saying the same thing. It's a different way of saying 20 is equal to 20. So now we have two different components to our 20, two different components here. So we can still say proportionally a number is directly proportional to a number. It's pretty cool, huh? Now, let's look at what happens when we change these variables. Because remember, I need to keep 20 is equal to 20. Let me add the symbols in here. Positive, 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 because direction matters. So look at this, how cool. I need 20 to equal to 20. But what happens if this component, 10, drops to 5? What if the acceleration, what if the mass goes down? Well, if the mass goes down and I need 20 to equal 20, the acceleration has to go up. So if my mass gets cut in half, my acceleration goes up. Makes sense. If you are pushing on a car that ran out of gas and you have 3 friends in the car, and let's say you gave an absolute max effort, you're pushing as hard as you can, and all of a sudden you're pushing and nothing's happening, and then all of a sudden your friends get out of the car. So you drop the mass, and maybe because they got out of the car, it starts to accelerate. So its acceleration went up proportionally to the mass going down. That's called inverse relationships. Two components, two factors on the same side of an equal sign are inversely related. If they're on opposite ends of the fence, they are directly proportional. They're directly related. But if they're on the same side of the fence, they're inversely proportional. Now, I say since time is on the denominator, then time is going to be directly proportional. In other words, you get into the cross multiplication stuff. But I'm just talking about in terms of F is equal to ma. These two guys being multiplied directly by each other are inversely related. As one goes down, the other one has to go up. As one goes up, the other has to go down, because we got to keep 20 equals to 20. Okay. Now, another cool thing about F is equal to ma, why it's so cool and important, is that it really has everything to do with physics and biomechanics in terms of application. Okay. Dr. Nels Madsen used to say, he's the guy that taught me 3D mechanics at Auburn, and his motion capture system was responsible for Gollum in Lord of the Rings. And Dr. Madsen used to say, all I do is apply F is equal to ma. That's all I know. He knows a lot more than that, but he was trying to humble himself. Well, he's a humble guy. He's like, F is equal to ma. That's all I do. F is equal to ma. F is equal to ma. So to show you some of the different things you can do with F is equal to ma, like basically you can have some basic ingredients, and based on what you do with those ingredients, you can make different dishes, different food things, right? You see what I'm trying to say? So some of the things you can do with F is equal to ma, okay? F is equal to ma. But we know acceleration is delta v over t, change in velocity over time. This is good review, because you guys are going to need to know the definitions and what this stuff means. Well, acceleration is this. So technically, I can take this, delta v over t, if that means a, well, then I can just replace a with delta v over t. And then I can do some cool stuff with it. I can cross multiply to bring the t over to the left side and m delta v over to the right. And now we have a new concept, impulse. How much time is my unbalanced force being applied? And a term at momentum, mass in motion. The mass of the object times its change in velocity. Delta v, mass in motion, right? Then you can do lots of stuff. E equals mc squared could be derived from F is equal to ma. It's crazy, but the point is you could do a lot of cool stuff with that equation of cause and effect, okay? So for the test, let's get to what you guys need to know. You need to know definitions. I'm not going to ask you guys to solve for X. You see Two-Face back there? What's up, gangster? Ooh, he's giving me the mean eyes. I'm gonna need a priest. All right, Two-Face. Take it easy. Ooh, never mind. I'm gonna cover him up. If I don't see it, it's not happening. Like when you were kids and you jumped in your bed and covered the sheets, the monsters can't see you when the sheet's over yet. You are going to need to know how to apply physics, not solve for X. And there's a reason I do this. One is, in the real world, you guys are probably not going to have the type of equipment that biomechanists have. Biomechanists have $50,000 fancy scales. We call them force plates. And biomechanists have electromyography systems, and biomechanists have motion capture systems. Some of these cost hundreds of thousands of dollars. You put the markers on and do all this. You ain't going to have all that. You know what you're going to have? You're going to have this, and you're going to have this. So you have to apply the physics, not necessarily solve for the physics. So you're going to have to understand cause and effect work, how different variables affect each other. As this goes up, that goes up. As this goes up, that goes down. That kind of stuff, right? So in other words, you know from the car analogy that if you're trying to push on the car to speed it up, if you lessen the mass, you have the potential to increase its acceleration. right? Think of a box of books. You got a box full of books. That's harder to accelerate the box of books, to speed it up and to slow it down. You take the books out, you lessen the mass, you can make that box go real fast. You can accelerate it. You can change its velocity a lot easier. Okay, so you got to see the inverse proportionality of mass and acceleration. Then you have to see the direct relationship of force and acceleration, right? And force and mass, because again, if I decrease or increase the mass, then it's going to come back to making it easier to accelerate. I decrease the mass for the same force. For the same force, decrease the mass, it makes it easier to speed it up and slow it down. Increase the mass makes it harder to speed up or slow down. So that's what you guys are going to have to understand, is directionality. When we get into F is equal to ma, you have to also understand directionality, right? So positive leftover, positive unbalanced force, I have to be positively accelerating. Negative unbalanced force, I have to be negatively accelerating. And that segues into the next part of the lecture. And that is, what does it actually mean to positively or negatively accelerate? So we're going to have the conversation on the right side of Newton's second law, the acceleration part. And we are going to have to understand that there are two forms of acceleration, because acceleration is a vector. We have positive and negative accelerations. Newton's law is F is equal to ma, not F is equal to ma, and sometimes F is equal to md. What I mean by that is acceleration does not necessarily mean to speed up. It can, but Newton didn't say accelerate means speed up, decelerate means slow down. Newton never used the word decelerate. It's a made-up word. I mean, all words are made up. But the point is that we don't have the term decelerate. The problem is that because people call the gas in a car the accelerator, by default we say, oh, accelerator speeds up my velocity in the car, so acceleration must mean to speed up. But that's not the case. Acceleration, being a vector quantity, has direction. So you have positive acceleration and negative accelerations, okay? Now, the crazy part is that positive and negative acceleration only mean directionality, meaning that if I have a negative leftover force, my acceleration is going to be negative. If I have a positive leftover force, my acceleration is going to be positive. However, positive leftover forces can speed you up and slow you down, not at the same time. Negative leftover forces can speed you up and slow you down, not at the same time. I'll give you an example, okay? If I toss this ball up in the air, okay? Now, I'm going to define what I'm talking about. I'm talking about the time, the start time, the stopwatch, right when the ball leaves my hand. What are all the forces that the ball feels when it leaves my hand? Use my pen. In biomechanics, we look at kinetics with something we call a free body diagram, meaning that we are going to draw the object free and clear of any other object and only account for the forces that that object may be feeling from other things. There's a reason we do that, is because it helps us not be miscommunicated by what's feeling what from each other. In other words, if I drew every object, it gets very confusing. If an arrow force is going up, well, who's feeling that? Is the object below it feeling it? Is the object above it feeling it? So we're going to draw an object, and my object is the baseball. Okay? So once it leaves my hand, this is a misnomer. I think people feel that once an object leaves your hand, it's actually you that's still influenced, and that's not true. What I mean by that is if you shoot a free throw, once the ball leaves your hand, you are no longer able to influence the motion of the ball. You lost all control of influence once that object left your physical touch. So if you shoot a free throw, and let's say you shoot it to the left and it looks like it's going to hit the rim, and you start leaning back to the right, that has no effect on the ball's motion at all. The ball's not going to look back and be like, what do you want me to do? Oh, you want me to go that way? And magically curve itself. Once it leaves your touch, you no longer have control of that ball's motion. So when the ball leaves my hand and I no longer physically touch it, and I'm not a Jedi, and my last name isn't Potter, this is the only force that the baseball feels. Planet Earth. Okay, I put mg, gravity from planet Earth acting through the mass of the ball. Okay, that's the only force that the ball feels. The ball feels gravity from planet Earth. Now, what direction is this force? Negative y. And it's the only force, significant force. You're like, well, technically wind. But say for tossing a ball up like this, wind, air is very negligible. So the point is that the kinetics of this example, the forces influencing the ball when it's going in the air, not after it touches my hand and right before it touches my hand, just that window, going up, then coming down, and we're going to leave my hand out of it. This is the kinetics. Now, if there's only one force influencing that ball, it's an unbalanced force. In other words, the leftover, once I add up, once I balance my checkbook, once I sum all the different forces, I'm going to get a negative number. And so therefore, if I apply F is equal to A, I know that this is a negative force. Negative, negative. So a negative y force is going to be directly proportional to a negative y acceleration. Now, you may be like, "What, dude, what happened to the m?" Well, this is just direct proportionality. The mass of the ball didn't change. It was a constant. Remember we talked about we infer physics all the time with the 40-yard dash. The displacement's the same, so all we do is look at the variations in time. Well, the mass of the ball is the same. So let's look at direct proportionality of force and acceleration. This is a negative force, and it's the only force the ball feels. So the acceleration must be negative. The ball is negatively accelerating as long as the only force influencing it significantly is the gravity from planet Earth. So what? This is so what? This negative acceleration is going to actually change this ball's velocity two different ways, because we know when it leaves my hand, it's going to go up and then it's going to come down. So let's look at that more in depth. What's happening as it goes up? What's happening to its speed, directional speed? What's happening to its velocity as it goes up? Isn't it slowing down? It's slowing down as it goes up. That's why, like, if you've ever been on a ladder and someone tosses you something at the top of the ladder, it's easy to catch it at the top. You know why? Because it slows down, and then at the very tippy top, there's going to be no motion right at the tippy top. It's a lot easier to grab and it's not moving. It's going to slow down going up. And then when it reaches the tippy top, it's going to change direction, and then it's going to start getting faster and faster coming down. It's going to speed up coming down. Okay. So the whole time the ball is negatively accelerating because of gravity from planet Earth, it's going to slow down while it's going up, change direction, then speed up coming down. both of these things happen because of one type of acceleration. It's pretty cool. How can something slow down while going up? Because it's negatively accelerating. How can something speed up coming down? Because it's negatively accelerating. Think about it like this. Gravity did both of these things. If you're having trouble seeing that, imagine a river current. So imagine there's a river and it has a strong current, okay? And the current is going, let's say, east to west, because obviously rivers don't flow up. So you have this river, okay? And let's say the current is going this way. I'm going to draw some arrows representing the flow of the water, okay? The water is flowing this way. There's an influence. Now, if I put a rubber ducky and I dropped it in the water is going to take the rubber ducky this way, okay? But what if I threw the rubber ducky upstream? I threw it this way. I gave it motion in the opposite direction of flow. Well, you know, eventually the rubber ducky is going to flow with the river. But before it starts to move with the river has to slow down the rubber ducky's motion this way, change its direction, and speed it up the other way. So the point is that slowing down the duck's motion this way is the same type of acceleration as speeding up the duck's motion that way. Why? Because the river flow is constantly this way. The acceleration matches the direction of the unbalanced force. So if we looked at the Cartesian plane, positive x, negative x, and the flow of the river is a positive acceleration, the rubber ducky will be positively accelerating, slowing down while it moves in the negative, and speeding up while it moves in the positive. Those are the same types of acceleration. Now, you may be like, whoa, how get a positive with a negative and a negative and a positive? Because acceleration and velocity are two different kinematic concepts. So in other words, I can be moving in the positive, but yet be negatively accelerating. The ball just showed us how we could do that. When the ball is flying up in the air, once it leaves my hand, it's negatively accelerating. It's slowing down while it goes up. So its motion is positive, but it's slowing down while it goes in the positive. So acceleration is because of something, cause and effect. What is slowing the ball while it goes up in the positive? A negative unbalanced force. So it's negatively accelerating as it slows down going up. So that's the big trap. We have to understand that acceleration is not motion. It's changing motion. But just because something is positively accelerating doesn't mean it's moving in the positive direction. It can, but it doesn't have to. Just because something is negatively accelerating doesn't mean it's moving in the negative direction. Okay? So let me give you the so what for this. Let me wrap it up in a pretty bow. Negative unbalanced forces that cause negative accelerations, they speed up objects moving in the negative direction. It makes sense. The river flow, right? If I was going to flip it and make it flow negatively, and I had a little rubber ducky that I drop in there, right? Speeding up in the negative. Negative acceleration, speeding the duck up to go with the flow. Negative acceleration. But negative accelerations can also slow objects down, but only when they're slowing it down when the object is moving in the positive. Okay, so I flipped it. Okay, so don't worry about this. So now it's flowing negatively. So if I throw the duck this way, and the duck has positive movement, it's moving in the positive direction, but it's slowing down. It's getting slower and slower and slower. Think about when you put on your brakes on your car, you slow down, but you're still moving in the same direction as you slow down. So that's what I'm talking about here. If the duck is moving this way and the river is slowing it down while it's moving in the negative, it has to be because of positive acceleration. Oh, I did the negative. If the duck is negatively accelerating, that means it's slowing down while it's moving in the positive direction. Remember, I flipped it so that I could do a negative example for you. Okay. Now, let's go back to our original one that we're more comfortable with. Positive accelerations can speed up objects in the positive direction and in the negative. So this is my so what for you guys today. Negative accelerations, because of negative unbalanced forces, can speed up objects in the negative or slow down objects in the positive. Meaning that negative accelerations, because of negative unbalanced forces, can speed you up if you're moving in the negative direction, or it could slow your booty down if you're moving in the positive. The same unbalanced force can do both of those things. The acceleration is the same. The direction of the acceleration is the same. Positive accelerations can speed you up while you're moving in the positive or slow you down while you're moving in the negative. Application time. Toss the ball up in the air. Once it leaves my hand, the only force influencing that ball is gravity. What direction is gravity? Negative. This ball is going to be negatively accelerating the whole time it's in the air and not touching my hand. The first thing, it's going to negatively accelerate as it slows down moving in the positive. It has positive velocity, but it has negative acceleration. That is important. Star check that. I tossed the ball up in the air. I gave it positive velocity, but its acceleration is negative because the unbalanced force it feels is negative. The same negative acceleration is going to slow the ball down until eventually it passes through zero velocity. There's going to be an instantaneous second where it has zero velocity at the top, but it's still accelerating. How do you know? Because if it wasn't accelerating at zero velocity, it would just stay floating up there. It has to come back down. Zero is just a number that it's passing through. So negatively accelerating going up, negatively accelerating coming down. In this case, that force of gravity from planet Earth is going to speed the ball up while it's moving in the negative direction. So again, that fits. In the baseball example, negative acceleration that the ball feels from planet Earth is going to slow down the ball while it's going up, change its direction, and then speed the ball up coming down. So the ball is negatively accelerating the whole time it's in the air and it's not touching my hands. Now, if it touches my hands, it's a different story. Let's look at what happens when the ball touches my hand. When the ball comes in contact with my hand, what does the ball feel now? Well, the ball still feels planet Earth pulling down on it, right? But now the ball is going to feel a positive push from my hand. So now the ball is going to feel two forces. Ball has negative velocity. It comes in contact with my hand. I slow the ball down as it falls down. Slow the ball down as it falls down. What kind of force slowed the ball down as it fell down? A positive force, a positive leftover, meaning that the push from my hand was greater than the pull from planet Earth. So the ball experienced a positive acceleration, even though it was falling down as it slowed down. The leftover force was positive. Positive unbalanced force, positive acceleration. direct proportionality, directionality as well. Positively accelerate the ball as I slow it down coming down, change its direction, then continue to positively accelerate the ball as I push it up. I speed it up going up. So the entire time the ball is in the air, it's negatively accelerating, both going up and coming down. And the entire time the ball is in contact with my hand, it's positively accelerating. Now I'm talking about this, just tossing the ball up in the air. When it's out of my contact, it's negatively accelerating. When it's in my contact, it's positively accelerating the entire time. Negative acceleration for the ball, slowing down as it goes up, speeding up as it comes down. Positive acceleration from my hand, slowing it down as it goes down, speeding it up as it goes up. You see how that works? All right. I want you to comment today, okay? Do some comments. Today's keyword to see if you did this lecture is got it with a colon or semicolon. If you accidentally put a semicolon or you don't know what the difference is, I understand. I have dyslexia. I don't know the difference either. Got it with a colon or semicolon. Also, take advantage of the questions. If you have questions, take advantage of comments. I'm thinking about doing a early morning because I have to do it before my boys get up because it's chaos over here. So I'm thinking about doing a setting up where I would tell you guys, hey, I'm going to do the biomechanics lecture Monday, and I'd love for you guys to join in live on YouTube where you can ask me questions and I can kind of clarify some things, all right? So keyword confirmation is got it with a colon or semicolon. You guys have a good weekend.